So one more topic I want to broach about fluid power systems is the area of electrohydraulics. And this is an area where, again, we could spend a lot of time. There's a lot of really neat things we can do with electrohydraulics, the controls, and the ability to do some pretty amazing stuff is here. This is where it really gets fun in terms of design for opportunities and so forth. But I at least want to look at some of the fundamental components when we talk about electrohydraulics. What are we talking about? Now, I've already mentioned a little bit about this when we looked at the directional control valves. I talked about how we can put a solenoid on the end of those spools and move those spools electrically. So we can energize a magnetic coil, and that's going to physically move those spools back and forth. And that's essentially what electrohydraulics is. And you can see an example of a couple valves there, different kinds of valves. The one on the right there is a typical spool like that we looked at that would slide back and forth, and we have a coil on either end of that to energize it. The one in the middle is a block, and this is, you see those pieces on to the left of the block over there. Those are what we call cartridge valves. And these are really neat. It's a relatively new innovation, but it's kind of some of the latest way that we're actually doing hydraulics, is that we build these cartridge valves like this. So there's all different cartridge valves. You can see that this is a coil on the top of it. There's an electrical connector. They all have an electrical connector of some kind there. And these are a cartridge that slides into this block and screws into it. So basically you buy a block that has different kinds of ports in it, and then you drop these cartridge valves into the block. So you can create whatever kind of valve you want. So you can get multiple centers and different types of spools in here with these cartridges. You can get relief valves and check valves and everything else. And so they drop into these cartridges. So you have all these custom made valves from relatively standardized blocks with standardized porting in them, and you drop the cartridges in the way they need to be. So it's kind of neat the way you build them up, and it gives a lot of flexibility in terms of design of systems, and it's easier for the fluid power suppliers because they don't have to provide a unique valve every time a customer wants it. They provide a unique configuration based on a number of off-the-shelf components with these different cartridges. Then they're also replaceable, so if they go bad, I can just pull a cartridge out, drop a new cartridge in, and it's not nearly as difficult as replacing the entire valve body, for instance, on a big valve stack. But now, looking at the electrohydraulics, there's really two fundamental things that we talk about in terms of control. And there's a simple on-off control, and then there's what we call a pulse width modulation. So if we go to a directional control valve here, and again, I showed this with this diagonal line on the actuator piece on the end, that indicates that this is an electrohydraulic valve. So there's a magnetic coil there that's going to move this spool one way or the other to activate it. But the question is how we do it. An on-off control says, all right, if this is a 12-volt spool, which I would probably have on a mobile machine, then I'm going to throw 12 volts at it. Whatever current it draws is going to create enough magnetic force, and it's going to slide that valve. So it's actually going to move this spool from one position to the next. And if I energize it the other way, polarize in the opposite direction, or if I have way off. Well, sometimes I want to be able to control the flow a little bit. So, and I can do this with a lot of mechanical valves. If I have mechanical actuation on a thing, I can pull it part way. So I can, just open the valve a little bit, let a little bit of flow through. And so I'm kind of doing some flow control and control how fast the load moves. But I can also do that with these valves. Now we'll also see another symbology with some of these valves. So we'll throw a horizontal line in between the ports that go to this valve like that. So I'll still have the 4 ports going into the valve, but we don't show them on the circuit connected directly to the valve. We show them kind of floating, and it gives the idea that this valve is going to float there. It's not really connected directly to those ports. And this typically indicates to us that this is what we call a PWM valve. PWM stands for pulse width modulation. Pulse width modulation. This valve is designed with the capability that I can just move it a little bit. And if I move it just a little bit, I'm going to allow a little bit of flow to go through these arrows, either straight or crossed, however they're configured there. So I can just slide it a little bit, let a little bit of flow. I can slide a little bit more, let more flow, let it come back, so I can control the flow rate at the same time as I control the direction in the case of this particular valve. All right, so how do I do that? What is pulse width modulation? And here's where we cross over with your circuits class, and you may have already talked about pulse width modulation in your circuits classes. But think about a square wave. So this coil that I put on here is still a 12-volt coil. So the wires that come off of it, I got to put 12 volts to it. So plus 12 volts or ground, okay? So that's what I got to do, put 12 volts to it. Let me clean that up. 12 volts and ground. When I hit that coil with 12 volts, it's going to energize it enough to move that cylinder. And if I do that, just throw 12 volts on and leave it, that spool is going to slide over and it's going to act like an on-off valve. But now what I'm going to do is what we call, I'm going to dither that valve, which means I'm going to send a square wave at it. So I'm going to turn the valve on, give me 12 volts, and then turn it off. And I'm going to turn it back on and turn it off, okay? And I'm going to do this really fast. Typical dither frequencies for a lot of valves, and this varies by valve design, is usually about 100 hertz. So the frequency of this square wave is about 100 hertz. Now, I send it that fast, I'm also going to control the duty cycle on this valve. So the way I've drawn that signal there, that's about a 50% duty cycle. So it's on for about half the time, off for about half the time. All right, I'm going to drop some vertical lines down here so that I have so I know where each waveform starts. If I want to move that valve over part way, I'm going to control the width of this pulse. So let's say that I just want to open that valve a little bit. So what I'm going to do is just hit this valve a little bit and then shut it off, and I'm going to leave it off. So I'm going to let the duty cycle go really, really low. So really short pulse, 12 volts, let it off, go like that. So you have a really, really small duty cycle, 10% or something like that, maybe, I don't know, so something really small. What that'll do is just kind of slap on the valve, so we're hitting the end of it real fast, like 100 times a second, like 100 hertz, I said, is typically what we do. And what that'll do is every time I hit that valve, it's going to slide it over a little bit, and that keep hitting it over and over again, it's going to kind of keep it floating and keep it stuck part way open. And if I can control this pulse width carefully enough, I can actually control how far that spool slides and control its how much it opens. So likewise, if I need a large flow rate, I could leave the duty cycle go big, so I could have a large duty cycle. So leave it on for a long period of time. I'm essentially sending more energy to that valve, which means it's going to stay on a little bit. It's going to move over a little bit further. The more energy in the pulse is going to make it slide over. So that is going to allow me to control the flow rate higher. Again, this is another level of control. It's where we have to get into a lot of microelectronics to control all these different functions, to be able to control flow rates. We use a lot of feedback in these systems, so we'll have flow meters and things at different points in the system to control flow rate. But this is the kind of stuff that allows us to do things like auto steer in agricultural machinery, for instance. So I can steer those front wheels smoothly. If I just have hydraulics that's on and off and it's jerky and jumpy, you know, that's not going to control well. It's not going to be comfortable for the operator. But if I can move the steering wheels, if I need to make a drastic steering adjustment, I can move the steering wheels faster. If I just need to make a small adjustment, I'll just make really small adjustments and I can control that flow rate and control it slowly. So there's where I can get smooth control, do auto steer and all that kind of stuff. So I have a lot of opportunities to do some neat things with that. But that's kind of where the next generation is in hydraulics, is all the electrohydraulics and different ways of controlling them and so forth. So if you get into this, if you're going to be working in fluid power systems and designing equipment, you're going to be working with electrohydraulic type of equipment. And so this is something that you'll need to look at and understand as we go there. So that's the end of the topics that we're going to look at. We'll have some practice on some problems But we're going to wrap up this. Again, it's a relatively short overview of a lot of things we could do in fluid power, and so there's where we are.